So in this video, we're going to continue with CC5, which is ionic bonding, and we're going to focus on the properties of ionic compounds. Okay, just to remind you, when we're talking about ionic bonding, we're talking about bonding between a metal and a non-metal. And if you're any way confused whether an element is a metal or a non-metal, you just need to have a look at your periodic table. By drawing this little staircase on your periodic table, it splits up the metals and the non-metals. All the metals are to the left-hand side, the non-metals are to the right-hand side, the exception being hydrogen, which is there in the middle, but it is a non-metal. So if you've got ionic bonding, you have got a metal, so say for example lithium, bonding with a non-metal, say for example oxygen. So two elements from opposite sides of that line. Okay, I could also have calcium, a metal, bonding with chlorine, a non-metal. That would be ionic. I could have potassium bonding with bromine, that's ionic. I could have iron bonding with oxygen, that would be ionic. I could have copper bonding with nitrogen, that would be ionic. Okay, so anything from opposite sides of the line, you've got a metal and a non-metal, it's going to be ionic. And I've written some examples here. Okay, in each example you have got a metal bonding to a non-metal. Okay, just to remind you how that actually works, I've just drawn out the following for the last example, aluminium nitride. So aluminium is in group 3, it is a metal and it's got 3 electrons in its outer shell. To get a full outer shell, aluminium will lose 3 electrons. Nitrogen's in group 5, so has 5 electrons in its outer shell. To get a full outer shell, nitrogen will gain 3 electrons. So if aluminium and nitrogen react, aluminium will give nitrogen 3 electrons. That leaves aluminium with a full outer shell and a positive 3 charge, and nitrogen will get a full outer shell and it will have a negative 3 charge. Remember, electrons themselves are negatively charged, so if nitrogen is gaining 3 electrons, it's gaining 3 negative charges, which is why it ends up with a -3 charge. Pay attention to the words I've written above. On this side, I'm describing aluminium as an atom, but on the other side, I'm describing it as an ion, and I've done the same with nitrogen. Okay, when they've got all of their electrons, they are atoms, but when an atom loses or gains electrons, we then refer to it as an ion. Ions always have a charge. In ionic bonding, metals always lose electrons and non-metals always gain electrons. So you're always talking about ions when you're talking about ionic compounds. I've written that here below, okay? Just the particles that are involved in ionic bonding are oppositely charged ions. You're not going to be talking about atoms, you're not going to be talking about molecules, you're going to be talking about ions when you're talking about ionic bonding. Because they have opposite charges, the ions are attracted to each other. So you've got aluminium with a +3 charge, nitrogen with a -3 charge. Opposite charges attract, and you end up with a really strong attraction between the ions, and this attraction is called the electrostatic attraction, okay, and it is very strong. If you were doing this reaction between aluminium and nitrogen, you wouldn't just have one aluminium and one nitrogen. You would have billions of aluminium atoms at the start, billions of nitrogen atoms at the start, to form billions of aluminium ions and billions of nitrogen ions. And because you've got so many, we describe the structure of ionic compounds as giant. Okay, that word giant there just implying that the structure is huge. It's huge because you've got billions of ions. So the 3 words that you would need for the structure of an ionic compound is giant ionic lattice. Giant ionic lattice, the structure of ionic compounds. When I was writing the formula for aluminium nitride, I would just write it as AlN, but this formula is a ratio. It tells me that I've got the same number of aluminium ions and nitrogen ions, but it doesn't actually tell me how many I've got. If I had 2,000 aluminiums, I would also have 2,000 nitrogens. If I had 2 million aluminiums, I would have 2 million nitrogens. This formula serves as a ratio. In reality, you've got billions of ions, which is why we describe the structure as giant. So if you were asked what is the structure of sodium chloride, you would say giant ionic lattice. For magnesium oxide, you would say giant ionic lattice. For iron sulfide, you would say giant ionic lattice. All ionic compounds have a structure that is giant ionic lattice. As well as knowing the structure, you need to know the properties of ionic compounds. And again, you're not going to study individual ionic compounds. You're just going to look at the properties of all ionic compounds, and you'll apply the same properties to whatever compound they ask you about. And the two properties that you need to know is you need to know that ionic compounds have high melting and boiling points. They are solid at room temperature. And you need to know that they can conduct electricity when they are molten or aqueous. These two properties apply to all ionic compounds. So if you were asked for a property of aluminium nitride, because aluminium nitride is ionic, you would say it's got a high melting and boiling point and can conduct electricity when molten or aqueous. You would give the exact same answer if you were asked for a property of magnesium chloride or iron sulfide or any other ionic compound. As well as knowing these properties, you also need to be able to explain them. So we're going to look at the high melting and boiling point one first, which means they are solid at room temperature. We just said that the attraction between the oppositely charged ions is very, very strong. If the particles are strongly attracted to each other, then the particles will be held very tightly together. If you look at your particle diagrams for a solid, liquid, and gas, if the particles are really attracted to each other and they're going to be held very tightly together, then that means that your ionic compounds are going to be solid, because in solid, the particles are tightly packed and all of the particles are touching, okay? Because there's a strong attraction between the particles, they're going to be really close together and they're going to be a solid. So that's why ionic compounds are solid at room temperature, because the particles are so strongly attracted to each other. If I wanted to go from a solid to a liquid to a gas, if you just look here at what's happening to the particles, to go from a solid to a liquid, you need to pull those particles further apart. And to go from a liquid to a gas, you really need to separate the particles. If you've got a really strong attraction between the particles, then that means you're going to need a lot of energy to break those forces of attraction and separate the particles. Because you've got strong electrostatic attraction between the ions, you are going to need a lot of energy to overcome that attraction and move the particles further apart. If you need a lot of energy, you're going to need a high temperature. So that's why we say they've got high melting and boiling points, because you need a lot of energy in the form of heat to overcome these strong attractions and move the particles further apart. Other property you've got is conduct electricity when molten or aqueous. By conduct electricity, I mean it lets electricity pass through. Molten just means you've melted it, and aqueous means you've dissolved it in water. So they only let electricity pass through them when you've melted the ionic compound or you've dissolved the ionic compound in water. And we need to look at why that is. So if we look at the bottom, I've written the criteria that a substance needs to conduct electricity. And I've said it needs free-moving charged particles. Okay, so they must have charged particles, and those charged particles must be free to move. So if we look at our structure of an ionic compound, you do have charged particles. Ions are charged. You've got a positive ion here, you've got a negative ion here, so you do have charged particles. All ionic compounds contain ions, so all ionic compounds contain charged particles. But now you need to look at the other criteria. Are those ions free to move? For this, we need to go back to our particle diagrams. Can the particles move freely in a solid? The answer is no. In a solid, particles can only vibrate. Can particles move freely in a liquid? The answer is yes. Can particles move freely as a gas? The answer is yes. So when you've got an ionic compound, you've always got charged particles because you've got ions. But if your ionic compound is a solid, those ions are not going to be free to move. Therefore, it will not conduct electricity. However, if you took your solid and you melted it, so molten, or you dissolved it in water, you're putting your ionic compound into a liquid form. And in liquid form, you've still got your charged particles, you've got your ions. And in liquid form, those particles are free moving. Because they can move freely, they can conduct electricity. So what I've just gone through, this here, the particles, forces, structure, properties, they are true for all ionic compounds. So if you were asked For a property of magnesium oxide, you would say it's ionic, therefore it's got a high melting and boiling point and can conduct electricity when aqueous or molten. If you were asked what state is sodium chloride at room temperature, you would say solid because it's ionic and it's got a high melting point. If you were asked, can aluminium nitride conduct electricity, you would say not when it's solid because the ions can't move freely, but yes when it's liquid because the ions can move freely. So these properties that we've learned, they are true for all ionic compounds. I've written out model answers for typical exam questions, which I'm going to put on the screen now. And in these examples, I've used potassium oxide. Again, potassium oxide is an ionic compound. You've got potassium and metal bonded to oxygen and non-metal. If you're asked for properties, okay, again, it's the two that I've just gone through. Pay attention to this. You don't get two separate marks for saying high melting and boiling points, okay? They don't count as separate properties, all right? Explain why potassium oxide has a high melting point. These are the things that you would need to say. You need to talk about those strong electrostatic attractions. You need to say that it's between oppositely charged ions. You need to say that you've got a giant ionic lattice because that tells you that you've got loads and loads of forces to overcome. And then you need to mention energy. You always get a mark for energy. So the underlined parts are what you get your marks for. The mark scheme is quite strict on this, so make sure you're including all of those underlined points in your answer. Because potassium oxide has a high melting point, room temperature is typically around 25 degrees Celsius. 25 degrees Celsius is not a high enough temperature to melt an ionic compound. So when I say predict what state it will be at room temperature, it's going to be solid, because 25 degrees Celsius isn't enough to melt an ionic compound. And then at the end, why can it conduct electricity when molten but not when solid? And again, I've underlined the key terms. You have to say ions are not free to move, so cannot carry current. You get a mark for specifying the word current. Don't say cannot carry charge, it has to be cannot carry current. And then molten, so when you've melted your potassium oxide, the ions are free to move and they can carry current. So these examples here, as I said, they are true for all ionic compounds. If you've got a metal and a non-metal, then these answers will be applicable. And the underlying parts are the things that you absolutely have to include. So to test your understanding of what we've just gone through, have a go at the following questions. Just press pause, do the questions, and press play when you're ready to see the answers. Okay, so I've filled in the answer. For the first one, they just want to know how a sodium ion and a fluoride ion form. So sodium is +1, that tells you that sodium loses 1 electron. Fluorine is -1, that tells you fluorine gains 1 electron. But to get your full 2 marks, you do need to say that fluorine gets that electron from sodium. Or you could say sodium gives fluorine 1 electron, or 1 electron is transferred from sodium to fluorine, but just something that implies that the electron is transferred. The next one, about conducting electricity. When molten, the ions are free to move and carry current. Make sure you're using that phrase, carry current, in your answer. As a solid, the ions are not free to move. Don't say that the ions can't move. In a solid, ions can vibrate, but say that they are not free to move. What is an ionic bond? You'll get 0 marks for saying the bond between a metal and a non-metal. Your definition is written here. These are the only things that will pick you up marks. The last one, which of the following is a typical property? Ionic compounds have high melting points, okay? They don't conduct electricity when they're solids, and they do when they're molten, so both of those points are incorrect. They don't have low boiling points, they have high melting and boiling points, so your answer is D. There's one other question that I want you to have a go at. This is a 6-mark question, and you have to put all of your knowledge of ionic compounds together. It tells you that magnesium reacts with oxygen to form magnesium oxide, and it gives you the electron configuration of magnesium and oxygen. It wants to know in terms of electrons how magnesium and oxygen react, and it wants to know, that's all. Actually, that's all it wants to know. It just wants to know how your, no, actually, I don't want you to do that question. I want you to do this question instead. So this again, is again about magnesium and oxygen. But for 6 marks, explain how magnesium reacts with oxygen and then explain why it forms a solid with a high melting point. So have a go at that question. Press pause, do the question, and then come back for the answer. Okay, so I've written an answer, okay? It wants to know how magnesium and oxygen react. So my first point is just about the transfer of electrons. Magnesium loses 2 electrons because it's in group 2 and forms Mg2+. Oxygen then gains those electrons, so it gets them from magnesium and forms oxygen 2-. So that's how they react with each other. I then need to describe why the solid that they form has a high melting point. If I'm talking about a high melting point, I need to talk about the strong attraction that holds those ions together. So I've written that the oppositely charged ions are held together by the strong electrostatic force in the giant ionic lattice. And I'm mentioning giant ionic lattice because that implies that you've got billions of ions all being held together by this very strong force. Because this force is strong, you need lots of energy to overcome the attraction, which makes it a solid at room temperature. So for your 6 marks, you'd get a mark for talking about the strong electrostatic attraction, you get a mark for the giant ionic lattice, you get a mark for lots of energy, and then you'd also get your marks for saying that magnesium loses and forms Mg2+, and that oxygen gains the electrons from magnesium and forms O2-.